Can you see it?
Yes, that's great.
Okay, yeah, hello everybody again. So this is the title. Sorry, the title has changed a bit. So the title now is the Neural State Machine for Character Scene Interactions. So this title is our paper that was presented in Psychophasia last year, and but I will cover our previous work as well. So it's just that there's a bit more focus on this topic. Okay, and so this is going to work with my students, Sebastian, her, and my colleague Jun Saito. And some of the contents are done by Daniel Holden, which is my previous student. Okay, and so here, what we are interested in is like learning these interactions of like manipulating objects or interacting with objects in the environment. And so here is a scene where from this game where the character is like carrying a box. You can see that the interaction with the box is pretty simple and not very physically plausible. And so we wish to like improve these kind of like object manipulation type of movements here. And so this is another scene from the Sims 4. So you can see here the characters are like guided to sit on these different chairs. And when you see the movements of the sitting down, they look okay, but you can see that the transition from standing to sitting is somewhat like quite uniform, where in the real life when you're like sitting on a chair, actually this transition is happening more smoothly rather than just standing in front of the chair and just sitting down. And so this is another scene from the GTA. And here you can see a bit better interaction with the character and the door. So you can see that the character is like using his hand to press the door and open, and you can see that the motion's well synchronized and you can see a nice transition from walking to opening the door. And so we wish to like learn these kind of movements rather than like hand tuning the system to produce these movements. Yeah. Okay, and so so this kind of interaction with objects or the environment, there are multiple challenges. And so as you see here, so the first one is that it requires a very precise control because the hand must be brought to some specific location in the environment, or like when grasping objects, you don't want the hand to be like, somewhere like penetrating the object or like not grasping the right location. So a precise control is needed. And also, as I said before, these transitions between various motions is very important, especially like for like standing, walking, and then sitting down. According to which foot is like stepping, the transitions is going to vary a lot. And so we wish to be able to produce all these variations of these transitions. And thirdly, this low-level control and high-level control is needed. I will describe this a bit more in detail later on, but usually when controlling a character, maybe we use the gamepad and the joystick for guiding character, but for this kind of like a very complex interaction, it's probably like not so easy to control the character by the joystick or something. So a bit more high-level control is needed. And fourth is this, we need to interact with objects which has lots of concavity, and so the motion needs to be very well planned so that the body doesn't glide or penetrate through these objects. And also like there's lots of variation in these objects like the chairs or desks, so the character needs to be adapting well to all these geometric variations. Okay, and so let me describe our framework here. Okay, and so this is like a demo video of our system. So here, as I said before, so the user has high-level control. So the user can like guide the character by like clicking the object. Also, here's like a low-level control, so you can use the gamepad to guide the character as well. Okay. And so you can do things like carrying, and holding objects. And when there's an obstacle, the character can avoid these obstacles while walking. And if there's a door, it can open. And again, this is like avoiding the obstacles. And yeah, carrying objects like you see here. Yeah. Okay. And so let me describe a bit about some previous work. Okay. And so here, this is like showing some clip of this motion graph plus system. So you can see it's a similar system. So you can grasp an object and carry it to some target location, and then like, guide the character to different locations. And you can also do motions like sitting down on the chair. Okay. And so this system is based on like doing some segmentation of various kind of movements and aligning the motion along the timeline, and then doing the interpolation between them by using functional PCA. Also, like transitions from one motion to another is like implemented using Gaussian processes. So it's a very hand-tuned system. So all the procedures of like, segmentation and alignment and interpolations done one step by another. Lots of manual, intervention is happening for achieving this system. Yeah, and also because they use these kind of like Gaussian processes for the interpolation, the scalability is not very high. Yeah, so that's where that was the issue. Okay. And so in like a few years ago, so we tried to implement this neural network-based character controller. So here is this, we proposed this phase function neural network. So we capture a lot of motion of like walking over different objects and walking and running kind of movements. And from this kind of like unstructured data, we propose a character controller that can learn from these kind of movements. And once the system is trained, so the user can like use this kind of like a gamepad to like guide the characters to interact with these different geometries like you see here. You see the characters like adapted to the height of the terrain. Okay. And so that's what we did before. Okay, so and so this model is like a it's a time series model. And so what we do is that given the previous frame of the character and some user control signal, so that is like reflected on this trajectory on the ground, so the direction of the character or like the velocity of the character is and given to this to this black box controller, and then it predicts the next pose of the character. Yeah, so given the previous pose, it predicts the next pose, and then this next pose is going into the input of this controller again to like generate the next pose again. So we do this on the fly in real time, and then we will be able to generate a character animation on the fly, so we can apply it for real-time applications like computer games. Okay. And when doing this, what we do is that we have like this trajectory on the ground, which is coming from the user input, and also we give the height of these locations so that the system understands the geometry of the terrain, and also like we give like information like the joint pose and the joint velocities. These are from the previous pose. And then also this input these trajectory information, and then the system outputs the joint positions, velocities, and rotations for the next frame. Yeah, so doing this over time. And so if we just use on the fly systems like LSTM or like maybe just an ordinary feed-forward neural network, and for this kind of time series prediction, what often happen is like that you see these kind of like foot sliding happening. So the system is not really interpolating these poses very well. And So this happens quite often, especially when you're like doing some transition from like walking straight to like turning, or like to straight walking to backward walking kind of transitions. Okay, and what we can imagine what is happening is that so say we have like a walking motion where these, these red dots are like the poses in the high dimensional space of this walking motion. Because it's a walking motion, it's a cyclic, yeah. And say we have like a side stepping motion, which is like side stepping, which are again visualized by these blue dots here. Okay, and in the high dimensional space, these motions or poses are somewhat like quite similar. Sometimes very different. And then we just dump all these poses into the system to predict the next pose. Actually, the system gets confused, and probably these poses are not very well aligned in the high dimensional space. And then when we just dump all these poses into the system, then the system can has difficulty figuring out which poses should be interpolated which in order to generate the pose that is desired by the user. Okay, and so in order to cope with this problem, so we propose to use this phase. Okay, so the phase label. So the phase label is like defined for this kind of locomotion. So it's it's set to 0 when the right foot is landing onto the ground. When the left foot lands onto the ground, it's defined to be pi. And when it comes back to the original pose where the right foot landing onto the ground, it's 2 pi, yeah? So now for all these locomotion, we can introduce this phase label. And then actually, this is very useful for aligning all these different locomotions, because in most locomotions, you always have this pattern of stepping on the left and then stepping on the right. So we have this alternate sequence of the foot contacts happening. Okay. And by introducing this phase label, what we can do is that for these different motions of sidestepping or walking, we can align them well by using this phase label. And now, so we will be able to have a correspondence between all these different poses and these different locomotions, yeah? And as we have this correspondence, which is based on the foot contact, we can naturally, transition from these different locomotion from one to the other. So even these motions of the side stepping and running is very different. We will be able to gradually switch from one motion to the other by moving along this phase labels, yeah. And then so we can use this for interpolating between various locomotion styles and then animate realistic character motion. Okay, so what we did in this phase function neural network is that we introduced a framework, an architecture, that a time series architecture for doing this inside the system. Okay, so given so this is a time series model. So this is a neural network. So we have an input pose and we have an output pose. Okay, so we give the pose in the frame I as the input, and then the neural network predicts the pose for the next frame, this I+1. Okay, and so in the if this is a feed-forward neural network, but the difference of this phase function neural network and the ordinary neural network is that the weights of the neural networks are not constant, but they are changing according to the phase. Okay, so what we do is that we prepare 4 control points over here. Okay, that is the form of the neural network weights of this main neural network. Okay, and so this alpha 0, alpha 1, alpha 2, alpha 3, they are like a matrix that is representing the weights of this network, yeah? And what we do is that given the phase, we are going to do a blending between these 4 control points, okay? And then compute a unique neural network weight for this main neural network, yeah? According to the phase, yeah? So we use this Catmull-Clark, not the Catmull-Rome spline for interpolating these four control points. So this phase is again changing from this 0 to 2 pi, and given the phase, these 4 are interpolated, and then that computes the unique weights for this phase, yeah. And then we can animate the character. So the advantage of this system is that, you know, even though we dump all the poses into the system, there's not going to be any interpolation of poses of different phase. Yeah. So the phase for like pi is always the, you know, it's always the pose of phase pi that is going to be interpolated to generate the pose for this phase. And so in ordinary cases, if we just dump all these motions together, there's a chance that these phases of like 0 and phase of 2 pi, or like phase of, you know, pi, going to be blended together just because the pose looks similar. Yeah. Because if even the pose is similar, if the motion is coming from different locomotion, there is a chance that they you know, they appear similar by chance, but actually they are of different phases. If you blend them together, that has more chance for this foot sliding to be happening because they are poses from the different timing. Yeah, so that's what can be avoided by introducing this idea. Okay, and so this is like another urban scene by this phase function neural network. So you can see that the character is like walking over these stairs, and because this green line is like, you know, stopping, blocking these dots to like penetrate through, you can avoid the character to hit these walls or like fall down into the hole. And here is like, because this dots on the side, they are analyzing the geometry of the environment. You can see that the character is like trying to keep balance while walking over this narrow beam, because these heights of these dots on the side were very low and the ones in the middle were high. So it can recognize this kind of a beam. And again, you can see it's like adapting to these stairs now. Okay. And yeah, okay. And then we introduced this mode adaptive neural network in 2018. So this is like animating the character to like this the quadruped character to walk and jump and do these kind of movements. Okay, and again, it's an interactive system, so the user can specify the direction and the speed of the character, and then the dog automatically adapts to generate the desired motion. Okay. So the one difficulty of these kind of quadruped character control is that they are multiple, you know, the way that the character walks changes according to the speed of this locomotion. Yeah. So when the speed is very low, this walking mode, then you can see that the left and the front leg and the back leg, they are quite synchronized, and so there's the left and the right legs, they are like there's a phase shift of about pi. Yeah, but on the other hand, when you increase the speed and then we switch to the trot, you can see here that you know, the front leg and the back leg, they are not synchronized now, but there's a phase shift of pi. And then you further increase the speed, then the left and right foot start to get synchronized. You can see that there's the phase shift is gone now, so the left and right leg are landing on the ground at the same time. Yeah, and also the front and the back leg, they have a phase shift of pi. Yeah, so all these according to the mode of the locomotion, then these foot contact pattern is going to change. Okay, and so if we try to apply the phase function neural network for animating these kind of locomotions of quadrupeds, there's going to be a problem, because there's going to, you cannot first you cannot define a good phase label for all these different locomotion modes. Yeah, and one simple naive approach is to like define the phase label based on just one leg on the front. Yeah, for example, the right leg in the front, you can define a phase based on when the foot contact is happening, but just based on the front leg. Yeah, and then if you try to train this phase function neural network by using this phase label, it's going to produce bad results because all the motion is just synchronized based on the front leg. And when you try to animate this kind of like a turning motion, you can see that the back legs are very stiff, the front legs are okay, but not very good. Yeah, so here in this mode adaptive neural network, we are managing this problem. So you can see that the back legs are now walking okay. And so for this mode adaptive neural network, what we did is that we changed the architecture a little bit, okay. And so again, it's like a time series model. So you give the previous pose and then it predicts the next pose. So that's done by this main neural network, okay. And this again, this main neural network, it's the weights are not constant, but it's like interpolated by these 4 control points. So the 4 control points in the form of this weights of this neural network, okay. Each of them is a matrix. They're interpolated and blended together to compute this, this weights of this neural network that predicts the pose in the next frame, yeah. And so that's all, again, same as the phase function neural network, but the difference is that previously we were interpolating between these 4 control points using the phase as a variable, yeah. But here, what we do is that instead of doing that, the blending weights of these 4 control points is computed by using the pose and the velocity of the feet of this character, okay, as the input, yeah. So using the foot velocity and the foot velocity as the input, the blending weights of these 4 control points are computed, and then that is used for predicting the next pose from the previous pose. So in this case, this feature of the foot velocity is very helpful because you can see that in all these different locomotion modes, the velocity are going to be very different, yeah. And so, for example, for when you compare the walk to this trot and the trot to the gallop, okay, so you can see that the foot velocity is very different, yeah, because you can see that the synchronization is going to change, yeah. And so that's a good feature for like this deciding which of these expert weights, yeah, how these expert weights should be blended together to generate this weights for this motion prediction. Okay, and so that went well for this quadruped character control. So you can see here, yeah, so the dog is moving around based on the user input. So again, as I said before, the character is controlled by this gamepad, and there's also a jump mode. You can press the jump button to let the dog jump and also sit down. Yeah. Okay, and so that's the previous work, yeah. And now let's go to this neural state machine. So those again, it's a similar, very similar architecture. So here, if you remember, we wanted to generate this animation for the character interacting with objects, yeah, or the environment. Okay, and again, it's a time series model. So you have you give the previous pose and also some information of the environment as the input, and then it predicts the pose in the next frame. So it's the time series model like here. You give the previous pose information, it predicts the next pose. Yeah, and okay. And so, as I said before, so we try to like, generate this interaction with the environment. So we have like sensors that sense the environment information and the object information. Okay, so if we have a chair, we have this kind of a sensor that analyzes geometry. We also have a sensor that analyzes the surrounding obstacles so that the character can avoid all these obstacles. These goes into the system. Also, we have like something called this goal-directed control scheme that I describe later on. But so when the character is like interacting with these objects, we have try to guide the character from the goal instead from from the egocentric route of the character. Okay, I will describe a bit more later. And then so these data and also like some action labels are given. So this we have to manually provide it, but we also like say, okay, this guy's like sitting on the chair. This guy's like trying to carry an object. For the training data, we add this kind of labels, and also we also provide some phase variable for all these different kind of motions, and then these are given into the encoder. Yeah, so these are given to the encoder, and all these information is encoded, and then it's passed to this motion prediction network, yeah, and to predict the next pose, yeah. And then again, so for the weights of this motion prediction network, we use this other gating network, okay, so that was similar to the mode adaptive neural networks. So this gating network is going to decide how we are going to combine these experts that is prepared, and then blend them together to calculate the weights for this mode prediction network. And one more thing is that when we are calculating the inputs to the gating network, so what we are going to give the phase of the motion and also the action label of the motion, yeah. And so we have like 6 types of motions here. So it's like standing, locomotion, running, and like sitting down, opening a door, and carrying an object. Okay, so we have these labels, and we also have the phase for each of these motions. So it's like changing from 0 to 1 according to how the motion is proceeding. Okay, and if we just like concatenate the input and then give it to the gating network, it doesn't work very well because these parameters are not blended very well. So what we do is that we calculate something called this Kronecker product, so which is like a cross product of these 2 variables, and then they are going to be this cross product is going to be given as an input into this gating network. Yeah. So that they blend more quickly. Okay. And so that's pretty much what this system is. So it's like we do this, have this end-to-end training. So it's trained all at once. Okay. Okay. And so now let me show how this data is prepared. So we have this motion capture data of this person like sitting down on chairs, like avoiding obstacles, or like carrying objects like you see here. So captured these motions using the XSense system. Okay, and yes. Okay. Yeah. And one thing is that okay, so we want the character to be able to sit on various types of chairs. So this is a bit of an issue. So there can be lots of different chair models. Okay. And so for each for one chair, we have to capture like lots of motion where approaching and sitting, or like with different transitions for like from sitting from the right foot or from the left foot, or from the left side or the right side, approaching from different directions. So for one sitting motion, one chair, we had to capture like almost 100 motions, yeah. So that's quite a lot of movements, yeah. And so if we want to like capture this for like 20 chairs or like 12 chairs, that's increasing the data size quite a lot, and also like it's going to increase the training time quite a lot, yeah. So that's probably not affordable. And so for coping with this, we propose some data augmentation pipeline, so which is not very complicated. And so what we do is that, okay, so for this sitting down motion, we are going to like analyze where the body is going to be in contact with the object. And so for these different body parts, so we are going to calculate their trajectory. Yeah? And now when we switch the chair to a new chair, like you see over here, okay, we are going to find the corresponding points of these endpoints, these body parts contacting with this chair. Okay, so we are going to like map it to the new geometry, like you see over here. Okay, and so this armrest and the bottom part, and like this foot contact location on the ground. Okay, now given this new chair, okay, we have these new locations, and then what we do is that we are going to adapt these trajectories of the body parts to so that they they adapt to this new chair. Yeah, so the contact points are going to be the same, and so you can see that the trajectory is going to be smoothly moving in the space. Yeah, similar to this original chair. Yeah. And once we give the trajectories for the end effectors for this new chair, we use reverse kinematics to generate the full body motion. Yeah. So then by doing this, we will be able to generate poses for the new chair. Yeah. And what we do is that, so we are going to randomly change this geometry of the chair for each of the frames of the motion, and then give this as the training data, yeah? And then well, by doing this, actually, we don't need to increase the size of the sitting down motion too much. We can just use the maybe same amount or a little bit more than the same original motions sizes. Okay. And so that's what we do. Yeah, so this is like a efficient data augmentation scheme. Okay. Okay, and now let me show this runtime control. So the low-level control is based on this gamepad. So you can see that the user uses the joystick to drive the character towards different directions. You can specify the orientation of the character. And we also have the high-level control. Here, we just click the object by the mouse, and then the character is going to do all these locomotion and approaching and then sitting down by itself. Yeah. So once you click this object, the system is going to do some autoregressive control. So the system is the same as before. So the previous pose is used for predicting the next pose. So this is going to be happening autoregressively. But by using this high-level character controller, so we are giving the goal of the location and the object to interact with as the input to the system, and then the system is going to just keep on producing the next pose by itself, okay, to generate the final animation. Okay. And so this, as I said before, we have this geometry sensors. So we have two types of sensors. One is this, blue sensor, this interaction sensor, that is analyzing the geometry of the object to interact with. Okay, so we have different chairs. So we're going to have a volumetric sensor. Okay, so according to how this voxel is overlapping with the geometry, so this sensor is going to be activated, and then this is going to be the input to the system. And similarly, we have this environment sensor, which is like a cylindrical volume around this character. Okay, and so when the object and the sensor is overlapping, then there's going to be activation of the sensor, and that is again going to be inputted to the system. Yeah, so passed to the encoder and then used for predicting the next pose. Okay. And so this is a scene where you can see that this, these different sensors are activated. So when you click the object, then the blue sensors are activated, and then it's going to be used as input. And you can now control the character by this low-level controller. So driving the character to different locations. And now you can click this target object, and then the character automatically approaches and put the object on the desk. Yeah. Okay. So by the way, is it okay, or were there any questions going on? By the way, I didn't really see the.
I've been keeping an eye on it, and I think we've not had any questions so far. But if people want to type in the chat, keeping an eye on it. But we can hear you perfectly. Thanks.
Okay. Yeah. So there might, because I'm doing this in the full screen mode, I wasn't sure if the.
No. I will interrupt if we get something.
Okay. So let's go back to the slides.
Oh, well, we do have a question from Ruben. Question is, can one modify the gait of the character?
Yes. So here there is going to be like a label for these different movements. So go to this, there was here, and so there was this action label.
Oh,
so
sorry, we can't see your screen.
Oh, you can't see the screen. Okay. Yes. So once I switch, I cannot let's see what's going on. Okay, now you can see it, right? I guess.
Yeah, perfect.
Yeah, and so like for this, we were giving the action labels for the gating network. So this sitting, standing, and running, walking. So we had this different labels. So you could like change the speed of the locomotion by this label here. Okay, is that okay?
Oh, yeah, perfect. Sorry, I muted
Great,
myself.
thanks.
And we've also got a question from Peter. Do you have to train each humanoid character individually, or does the learning transfer for these?
Yeah. So each individual, so this character, actually, this system is only for one character here. Yeah. So unfortunately, you cannot switch between characters. Similar for the previous ones as well. So all the characters are just trained on one single character. So you cannot really change the size of the character.
Great,
Yes.
thanks.
Yeah, so actually that's a good topic to work on. Yeah, there's some people also were asking, the industry people were asking that as well. Yeah. And where were I? Let me just go back. Okay, I wasn't sure where I was. Maybe I can. Okay, yeah, I think I was around here. Yes, and when we were doing this control, so we were using this gating network and then using it for activating these different experts, and then using it for predicting the next pose. Yeah, and so each of these dots are like representing the experts, different experts. So let's have a look at how these experts are utilized while the character is controlled. Yeah, and so here actually we plot the trajectory of how these experts are activated. For when you see the walking motion, you will see a unique cycle for the walking motion. For the running, you see another one. When the character is like sitting down, you see that it's converging to some expert that's probably corresponding to the sitting motion, and there's opening as well. So you can see some unique, usage that is happening. So you can see this in the animation here. Okay. So these kind of different activations happening. Yeah. Okay. Yes. Okay. Yeah. So that's probably fine. And so here is showing that this Kronecker product that I mentioned before is helping a lot. So you can see that when you try to like visualize the activation of different experts, when you use this Kronecker product, actually you can see that there's a switching of the experts nicely happening. While if you don't use the Kronecker product, actually this activation of different experts is not really happening, and then it's like producing some kind of like a foot sliding like you see over here, which is not very ideal. Okay. And so this is good. And then let me show some quick evaluation of the system. Okay, so here you can see that we can like use this high-level character controller to guide the character to do sitting motion or from one chair to the other. Okay, and so you can see it's adapting well. And okay, with the geometry sensors, you can see that the character can actually avoid this desk in the front of the chair when guiding the character. So when you're in the front of this desk, the character can avoid the desk to sit down on the chair. And so here you can see that the character was like walking to the side first and then sitting down instead of like just walking straight to the chair and then sit down. Yeah, so that would be so good. Yeah. And also, like, the character can adapt to the different sizes of the object. Yeah, so you see here. Okay. And so the system is quite interactive, so you can like drag the object to different directions, and the character can immediately, respond. Yeah. And so these are like objects of unseen geometry. So these objects are not shown during the training, but you can see that the character adapts to it and then just do the right motion. Okay, and so as a comparison to other architectures, so if we use this PFNN for like managing all these different types of locomotion, actually it doesn't work very well because all the motions, although the phase is similar, it's the same phase. If the motion comes from different classes, like sitting down and walking and like opening the door, they all dumped into the same system. Then even though the phase is aligned, it doesn't work very well. So you can see lots of shaking motion happening. And also this mode adaptive neural network actually doesn't work very well for the biped characters. So you can see that there's lots of foot sliding happening. While in this NSM, it's working better. Okay. And yeah, so this is a comparison to this LSTM. So the LSTM has this internal memory, and so that's very helpful for like preserving the previous history of what this character was doing. But on the other hand, so this is like an example where we are trying to switch from the sidestepping to the sitting. Yeah, but when we do this, so actually in our training data, we don't have any transition from the sidestepping to the sitting motion. And so that's going to be a problem for the LSTM, because in the case of this LSTM, because it has this memory, okay, and you want to like activate this sitting motion. If the memory state is always in this sidestepping motion, the system doesn't know how to transition from the sidestepping to the sitting if that's not observed during the training. Yeah. And so that's you have to like keep on sidestepping and gradually changing the memory until it reaches some state that it can start doing the sitting motion. So on the other hand, our system is a memory-free system. We don't actually have any memory. So when we do the switch from the sidestepping to the sitting, the character naturally, is be guided to do some other motions first and then sit down. Yeah. So in that sense, because we don't have any memory, we don't need to like expose the system to all different types of variation to like generate this kind of motion, which is advantageous. Yeah. So for the LSTM-based systems, actually, you need to do a lot of data augmentation. Well, not only for that adapting to different chairs, but just for the locomotion trajectory itself, you need to like generate lots of variations of the trajectories, and then so that the system can be more responsive to the instructions of the user. Yeah. So you need to expose it to various memory status so that the transition can happen more quickly. Okay, and so that was most of the things. And so in conclusion, so we propose these deep learning frameworks for synthesizing realistic character motions. And especially here, we were focusing on this character scene interactions, and we would adapt to these different geometry and type of objects by using these data augmentation scheme that we proposed, also using all these extra sensors as input. And so we have to use this phase. We are trying to use the advantages of using the phase as well as the expert control system by this MANN, and then try to generate this movements of adapting to different geometry and also locomotion types. Yeah. And so for the challenges that are remaining, so there can be like here we were like one problem of this system is that all the control signals had to be manually defined and labeled and then given to the system. It's good if there's a more general scheme that can manage different types of local movements and actions. Okay. And another issue is that the motion sharpness is going to be always lost when you are doing this kind of a blending between different movements, which is a bit of an issue. So we wish to search for some architecture that can preserve the sharpness of the movements. Okay. And so maybe like these GAN architectures can be helpful, and like also like more generative models could be useful for this kind of purpose. And so here we were using the phase labels. These had to be like manually defined for these different movement types, actions like sitting down or like opening a door. These are for aligning these poses at different timing, and so that was a bit problematic. And yeah, so maybe like other topics like multi-character interactions or crowd-based character animation could be interesting next steps. Okay. And so we recently did another thing about like for managing these kind of like multi-contact movements, where we like so previously we had a single phase for all the full body, but instead of doing that, we did is that we propose a way to like define phases for each limbs individually, yeah. And so and then use this as a input feature for the system to again as an input feature for the gating network. And so that actually works pretty well. And because like these kind of locomotions and like sitting down or carrying objects, usually the timing of like touching the object or like the sitting down, the foot contact and the ground is there's a wide variation, yeah. And so like instead of like aligning all the motions by a single phase, actually it's better to like define phases for the individual body parts and then like let the system like learn from this, yeah. And so that's what we did. We defined these phases for different body parts and like use this to like animate some motion. Actually, I can show for this. So let me do that. Okay. So what I need to do here is that first I play the video. Okay. And then I share the screen. Can you see it now?
Oh, yeah, that's great. Thanks. Okay.
Yeah, so this is a basketball scene. So the character is like, can you see it? Is it okay?
Yeah.
Okay. Yeah. So now you can see that this character is like this basketball is coming from some motion capture data, and then we train a system to like learn these movements. And so this is one of my students was doing internship at this electronic arts, and then they had lots of basketball motion. So we were like proposing this architecture for managing it, yeah. And so the main feature is that again we have these different phases for these different parts of the body. So like for the forelimbs and also for the ball, and we have these different phases, and the phases are defined based on the contacts happening between the limbs and the environment or the object, yeah. And then we can train the system to learn these basketball movements. And also like the interaction with another character as well is used as another feature for the system. And so the phases are like computed from the trajectories of the limbs, and like this is computed as a pre-process, and then it's given to the network. And we also have a generative control scheme for generating like different variation of movements, although the control signal is the same, yeah. Because this database actually is quite large, and so there's lots of variation of the motions. And what else? So can show that it's like, yeah, so this is also helpful for this quadruped character control. So even though you show very extreme character control signals, the system works very well. Also, we apply it for this sitting down motion and interaction. It works well. So you don't need to manually define the phase and like, align the motions, but it does it automatically. So that's quite useful. Okay. So, and that, and now I go back to the slides. Almost it's over, but I do this. So I stop that and then do this, and then go to the slides. Okay. Okay, and so that's pretty much all. So the work was done by these guys, and also Daniel Bowden. Yeah. So thank you very much for listening. Any questions?
Yeah, thank you very much indeed. Thank you. So this is where you have to use your own neural generator to imagine lots of applause happening, because we don't deafen the system. But thank you very much for the very interesting talk. To remind everyone, there's the chat button, which is the sort of little speech bubble-like thing, so you can ask questions on the side in the talk there. To kick things off, Sneaky, and I'll ask a question. I think you sort of touched on it, I guess, a bit at the end, but it's sort of two parts. Is kind of saying, the first is what level of curation do you sort of need of the data in terms of specifying the phases and things like that? Is it partly automatic or fully manual to label up the data?
Yeah. So that's a good question. So for for the phase function network, and that one was like, it was basically based on the foot contact. So that was almost fully automatic, although there was a bit of a manual tuning. So like you can like analyze the velocity and the height of the foot, and then you can like analyze whether it's in contact with the ground or not. But like in this kind of system, usually you need to specify the threshold, and then the threshold's not good, and then it makes some mistakes. So there's a bit of like a manual tuning for that, for the threshold values. And so for the neural state machine, actually this is much more time consuming, because you need to define the phase based on when the definition that is given by the user. So like for the sitting one, it's like when you're sitting in front of the phase is probably like the last step of the foot contact happening is when the phase is set to 0, and then when you're like the hip is contact with the chair is when it's 1. So then you need to like find a way to like manually, maybe semi-automatically, label the phases for these poses in the middle. So that's quite troublesome. So the last one that I was showing, this basketball one, is that one is trying to like resolve that problem. So it's basically doing it this more automatic fashion.
Yeah. Oh, that's great. And then my sort of other question was, so I think you talked a bit at the end about sort of like, if you've got something that's been trained very well, to avoid sort of repetition in terms of like there might be an optimal walking sequence and you just see that again and again and again. So do you sort of inject noise during training or during like test time to kind of introduce variations?
Yeah. So there's always this noise thing. So dropout type of noise is always added, and for like trying to make it more generalized. Yeah.
Cool. Great. So if anyone has any questions, type them in or shout them out. Now is a good time. Oh, there's one from Peter. Oh, well, do you want to unmute yourself and ask your question, Pete? That's fine.
Okay. Thanks, Taku. I really enjoyed the talk. I thought it's great work. I'm interested in it might be in the data already, and it may not matter, but I'm interested in the idea that two frames, successive frames, don't seem enough to get acceleration out. And thinking about perhaps the difference between kinematics, dynamics,
Right.
that sort of thing. So could you comment on that for us, please?
Yeah, I see. So the physics things is, yeah, for sure. Here we thing, yeah. So it's basically like just observing the kinematics, and like of course you cannot do things like, you know, increasing the weight of an object to make it heavy or something. So what you can observe is always what is in the data set. And like if there's some physics like jumping off from a chair or this kind of motion, actually the system can learn that because it's, I think usually it's very there's the previous frame and the next frame is somewhat unique, because it's following the rules of dynamics, yeah. And so even yeah, so for like if we want to do the data augmentation by using the physics, I think that's another potential way to go. And so like you can like try to like, you know, produce these effects by using physically based motion editing, and then use that as a training data with, you know, different physical parameters as an additional input into the neural network. Yeah, but I think this is yeah. So there's always a difference between this kind of a supervised learning, kinematics-based supervised learning, and, you know, physics-based control, such as those based on, you know, the reinforcement learning. So yeah, I think it's yeah, but physically based interactions are very interesting. I think doing this in the framework of this kind of a supervised learning is an interesting direction to go.
There's some interesting points there, especially I didn't think actually of the introduction of physics. I was thinking really more the introduction of a third frame, really. But certainly the idea of having some physical constraints. For example, if you jumped off a chair and you learned how to jump off the motion for jumping off a chair, maybe if you jumped off something higher, you would end up not accelerating all the way to the ground, but having, I don't know what would happen there.
Yeah, that's interesting. Yeah, so I think that will be the case for sure. So probably if you just have like a motion from jumping on from one type of chair, and then like if you like try to generate a motion from jumping off from the second floor or something, then probably there will be a very smoothed out motion happening. Yeah, that is like not really accelerating at all. Yeah. And yes. Well, but it's interesting if the system can learn such kind of you know, conservation of momentum, so that it generalizes better to like these kind of situations. That's maybe it's possible to like have a loss somewhat like that. Yeah, a loss based on this observation of momentum, and yeah, and then to try to make it more general. Yeah.
That's a very interesting thought. Yeah. So conservation of energy and momentum and other physical principles like that could constrain the system. Yes, that's an interesting idea. Okay, I'll mute back up actually, because I let somebody else take over if they want to.
Right. Yeah, I think like some people like doing these kind of smoke-based animation, or like the fluids, and these kind of people, when they try to introduce this kind of a machine learning approach, they should be using these you know, what loss functions based on the physics. Yeah, so that's interesting to think about. Yeah.
Thank you, Taku. That was a really good answer. Thank you.
I'm not sure if there are any more questions. I have another quick one that just on the sort of practicalities, Taku, I presume for lots of these sort of animations you've been showing, this is all sort of the real time at test time. You're doing real time interactive rates. Are there sort of very strict limits on what you can sort of compute for games and things like that? Presumably, you're not allowed to take up much time.
Right. Yeah, that's a good question actually. So when Sebastian was doing this this basketball thing, he mentioned that there's not really much CPU time left for doing these things, and it requires a bit more. Yeah, probably it can only be introduced in the next generation type of game consoles for doing that. So that was a bit disappointing to hear. Yeah, and of course we here can like use whatever computers for like accelerating system to animate the results. So yeah, so in these systems, it's like still like just a milliseconds or something to animate them. But it seems that in the game companies, the requirement is much higher. So that's yeah, there's some trade-off. Yeah.
Brilliant. Thanks very much. So final call for anyone if they have any questions to shout out now. Otherwise, I shall thank you on behalf of all of us very much for talking to us today, Taku. It's really great. Of course, normally we would show you around and give you some food for your troubles. So we haven't arranged, unfortunately, for a parcel of food to be delivered to you. But hopefully, when all this is over, you can come down and visit us as well.
Yeah, sure.
That would be great. But thank you very much indeed for your talk today.
Yeah, thank you very much for inviting me. Yeah, so it was good to talk to you. Yeah.
Cheers. Awesome. Thanks very much. And right, I shall stop the recording now. Very good.